Welcome back to Math 109, Plain Trigonometry. In this video, we're going to look at the trigonometric function values of 30, 45, and 60-degree angles. We're going to start with the 45-degree angle. So I'm going to draw a right triangle. And these two angles are both 45 degrees. Now, if you remember from high school geometry, that if we have those two angles being equal, the sides opposite of them are congruent. So we're going to go ahead and say they have length 1. And now, using the Pythagorean Theorem, we know that the hypotenuse has length square root of 2. So we'll go ahead, for the sake of reference, look at the 45-degree angle on the bottom. Let me just get a better 45 degrees out of that. So, the sine of 45 degrees is going to be the opposite over the hypotenuse. So that's 1 over the square root of 2. And usually we are going to want to rationalize the denominator, so we'll multiply both the numerator and denominator by the square root of 2. And we get the square root of 2 over 2. Likewise, the cosine of 45 degrees, that's also equal to 1 over the square root of 2. And it's going to rationalize in the same way. Do the square root of 2 over 2. And finally, the tangent of 45 degrees. That's opposite over adjacent, so 1 over 1. So that's just 1. So that's for a 45-degree angle. We also want to look at 30 and 60-degree angles. And for that, we're going to take a look at an equilateral triangle. And I'm going to make the side lengths of this triangle all 2. Now, another result from high school geometry, it's a corollary to the result we used for the isosceles right triangle. If this triangle is equilateral, it's also equiangular. So all three angles are the same, therefore they're all 60 degrees. So let's draw a line down the middle of that triangle, bisecting the angle at the top. And we can use another result from high school geometry that says that's also going to bisect the segment at the base of the triangle. So we'll take a look at that half of the triangle. So we have a 30-degree angle at the top, 60-degree angle on the right, and then the right angle. We know that this is length 2, this is length 1. We can apply the Pythagorean Theorem and obtain that the triangle is a height of the square root of 3. So now we'll go ahead and look at the 30-degree angle. We can see that the sine of 30 degrees, that's the opposite, 1, over the adjacent 2, so it's just 1/2. Likewise, the cosine of 30 degrees is the adjacent over the hypotenuse, so that'll be the square root of 3 over 2. And finally, tangent of 30 degrees is opposite over adjacent, so that's 1 over the square root of 3. And we'll rationalize the denominator, multiply both numerator and denominator by the square root of 3. And we get the square root of 3 over 3. Now, as far as 60 degrees goes, for sine and cosine, we can use the cofunction identities. Sine of 30 degrees is going to equal the cosine of 60 degrees. And the cosine of 30 degrees is going to equal the sine of 60 degrees. I also could have used the right triangle definitions here. Now with the tangent, we've got to do a little bit of work. We are going to use the right triangle definition to obtain this. So we note the side opposite of the 60 degree angle is the square root of 3, and the adjacent leg is 1. So that's the square root of 3 over 1, division by 1. We're not doing anything, so we get the square root of 3. So this is how we obtain the trig function values for the 30, 45, and 60 degree angles. These angles are used very frequently in trigonometry, so you will want to have these memorized for future reference. That concludes section 2.1 of our text. In 2.2, we will look at how to use these right triangle definitions to obtain trigonometric function values for any angle, not necessarily in the first quadrant.